Hello, welcome to this video. In this video, let us talk about diesel cycle. Now, the diesel cycle is an idealized thermodynamic cycle that describes function of a typical compression ignition internal combustion engine in which heat is added at constant pressure. And obviously, the fuel which we are talking here is diesel. So, it is also called as compression ignition engine, or the cycle is also called as compression ignition cycle. So, compression ignition, because the ignition here is happening by compression. All right. So, diesel cycle is an idealized thermodynamic cycle that describes functioning of CA engine, that too in which heat is added at constant pressure. Now, let us look at how a 4-stroke diesel engine works like. All right. There will be a 4-stroke, as we had discussed earlier also, that one is suction stroke, that is also called as intake stroke, then we will have compression, then power and exhaust stroke. All right. Now, during suction stroke, now we will have to make a distinct difference between a petrol engine and a diesel engine. In petrol engine, what comes inside is charge, that is air and fuel which was already mixed in the carburetor comes into the cylinder, whereas here we will receive only air. And while talking about compression ratio of SI engine or spark ignition engine or Otto cycle, we have always discussed that the compression ratio ranges from 6 to 8. That is because we cannot increase the compression ratio, even though we know that increase in compression ratio results in increase in efficiency, because the charge can auto ignite and lead to what we call it as knocking. All right. Here the knocking is different. Let us talk about knocking in later classes, but what comes in here is only air. All right. Air is coming in during suction stroke. All right. So, during the suction stroke, piston moves from top dead center to bottom dead center. Okay. This is what suction stroke is. Then during compression stroke, both inlet and the exhaust valves are closed. Of course, during intake stroke or suction stroke, only inlet valve is open, exhaust valve was closed. Now, as piston moves downward, there will be suction created or pressure drop created. Because of that pressure drop, there will be air which comes in. That is what is suction stroke, during which the piston moves from top dead center to bottom dead center. During compression stroke, both the valves are closed, piston moves from bottom dead center to top dead center. All right. Now, during which air is compressed to a higher temperature and pressure. Now, there is no problem of auto ignition here, because we are compressing only air. All right. There is no fuel. So, we can increase the compression ratio in a typical diesel engine, because of which the compression ratio of CA engine or diesel engine will be of the order 15 also. Now, during power stroke, what happens is that there will be fuel supply. Now, there is one more difference between petrol and diesel engine is this: there will be a fuel injector and there is no spark plug here. Now, why we have a fuel injector? Now, at the end of this compression stroke itself, the pressure and temperature of the air is so high that the moment we introduce the fuel inside to this combustion chamber, it auto ignites. So, typically a diesel engine should increase the temperature of the air to an extent or greater than that of the auto ignition temperature of the fuel. So, it auto ignites, we need not to provide any spark plug, because of which the ignition starts automatically. All right. Now, the moment the auto ignition happens, the piston starts moving descend towards the bottom dead center, or piston starts moving from top dead center towards the bottom dead center, and there is some portion of this total swept volume is that we are still supplying the fuel. This is what is very important in diesel engine. So, this is what we call it as, I mean, the volume where the fuel supply is taken care this volume we call it as cutoff ratio. I mean the volume ratio we will talk, but remember the total volume which we are talking about is swept volume, but there is small portion of volume where we are keep keep on supplying the fuel. So, that portion is very important in diesel engine, and remaining stroke will be power stroke. However, this total stroke is called as power stroke, but remember that some portion of this stroke is where we are also supplying the fuel, and at some point we will cut off the fuel supply. So, that we will talk about in while writing the cycle, the significance of it. Now, after that power stroke, of course, during power stroke both the valves were closed, and the moment we are executing exhaust stroke, piston was at bottom dead center, and exhaust valve is open, piston goes to the top dead center while pushing the exhaust products or combustion products outside. So, this is 4 stroke diesel engine. Now, let us try to write PV and TS diagram for the same. Let us try to write PV and TS diagram for a typical diesel engine. PV diagram. Now, first stroke is suction stroke. Now, how suction stroke happens we already know. Suction stroke is where piston travels from, let us say this is your clearance volume or top dead center, and there will be piston traveling from top dead center to bottom dead center. And during this we are assuming that this is going to be a constant pressure process, because the moment the pressure drops, concentrate on this suction stroke. During this suction stroke, we know that the pressure is not let to drop, because in reality it is like this, there will be a pressure drop and it is recovered by the air which is coming in, but we cannot model that. So, we are assuming that it is going to be a constant pressure process. Anyhow, we will call this as 0 to 1, alright. So, this is our suction stroke, and compression is from 1 to 2, that is again piston is traveling from bottom dead center to top dead center. And remember, during this stroke we are assuming that the process has to be reversible adiabatic, because we want to supply lesser work. So, this was our constant pressure process. Now, this is PV power gamma is equal to constant, alright. Now, very important, the moment we reach to this, now 0 to 1 was suction and 1 to 2 is compression stroke. Okay. Now, 2 to 3 is what? We are supplying fuel at this point. Now, the moment we start supplying the fuel, the auto ignition occurs and there will be expansion of this combustion products. So, that will push the piston downward, which means the heat is added, but unlike petrol engine, this is not at constant volume, because piston is allowed to move. That unlike petrol engine where air and fuel was readily mixed in the carburetor, and that is what we have compressed, and the moment we give the ignition source, that happens at a constant volume. But here the moment we supply the fuel, the combustion of that is already pushing the piston downward. So, it is not like constant volume, because instead of that we are modeling it as constant pressure process. Now, heat is added at constant pressure, very important. This is basic difference between our constant volume heat addition cycle or constant pressure heat addition cycle. In Otto cycle it is constant volume, because already fuel and air was mixed in the carburetor, and the moment we give the spark into the cylinder, it auto ignites in a moment of flash. So, that is like at the same volume only we have added the heat, but here the volume about which we keep on supplying the fuel. So, that is the volume about which we are adding the heat. So, that happens at a constant pressure process, or that can be modeled as a constant pressure process, because we are allowing the piston to move downward at the same time. So, this volume is very important. 2 to 3 is the volume about which we are keep on supplying the heat or keep on supplying the fuel. So, this is constant pressure heat addition. So, this is constant pressure heat addition. Now, 3 to 4 is an expansion, and remaining stroke will be modeled like similar to that, that is PV power gamma is equal to constant. and then 4 to 1 is again constant volume heat rejection. Actually, if we look at our cycle here, the intake stroke is we have modeled this as 0 to 1, compression stroke we have modeled this as 1 to 2. Actually, from here power stroke actually we have modeled some part of it as heat addition. So, this part is something like 2 to 3 and remaining this portion is 3 to 4, alright. Now, this portion is 4 to 1. Now, what is 4 to 1? The moment we are at bottom dead center, we open this exhaust valve. So, the moment this exhaust valve is opened, most of the energy or most of the combustion products is let out or pushed out because of the pressure difference. That is more or like constant volume heat rejection. So, we are modeling this as constant volume heat rejection. So, this is our cycle in a PV diagram, alright. So, constant pressure heat addition. Now, let us try to write the same in TS plot as well. So, TS plot as well. Okay. So, in temperature versus entropy plot. And remember this exhaust stroke is again 4 to 1, right. Now, this 4 to 1 is exhaust stroke, and this again after this exhaust stroke, this remaining portion of combustion products is pushed slowly out of it. Now, that will be again like 1 to 0. So, this cancels out. I mean, if you start talking about efficiency or work transfer, 0 to 1 gives you positive work and 1 to 0 gives you same amount of work, but it will be negative. So, this will be cancelled out readily. So, we can cancel this 0 to 1. That is why we never consider this process. So, we will write only this much, that is 1 to 2, alright. So, I will just write it, I will just rewrite it now, this in a, let us write. Now, there will be a compression, reversible adiabatic compression, that is 1 to 2, then 2 to 3, a constant volume heat addition, sorry, constant pressure heat addition, then we will have reversible adiabatic expansion, then we will have constant volume heat rejection. So, this will be our cycle. So, 1 to 2 is PV power gamma is equal to constant, 2 to 3 is pressure is equal to constant, 3 to 4 again reversible adiabatic expansion, then 4 to 1 is constant volume heat rejection. Now, let me write this as our heat supplied, this constant volume heat rejection, alright. Now, similarly, we will write the same in here. So, that will be 1 to 2 reversible adiabatic expansion compression, that is 1 to 2, then constant pressure also look similar like constant volume, then 3 to 4, then 4 to 1 is again volume 4 to 1, sorry 3 to 4, 3 to 4, 3 to 4 is reversible adiabatic expansion or isentropic expansion, then 4 to 1 is constant volume heat rejection. So, this will be 2 to 3 heat supplied and 4 to 1 heat is rejected. Now, let us derive the efficiency equation for this. Now, how do we derive efficiency equation here? Efficiency equation can be derived starting from here. Efficiency is given by 1 minus work net divided by heat supplied, alright. Now, work net is what? Work net is from first law of thermodynamics, heat supplied minus heat rejected by heat supplied. Now, this can be 1 minus QR by QS, and remember already we have used this negative sign. So, I do not want to keep QR in negative. So, 1 minus, what is QR we are talking? So, for constant volume it is CV dt. So, CV T4 minus T1. So, I told that we will go for highest minus lowest because already I have used negative sign here, divided by constant pressure, that is heat supplied here is at constant pressure. So, Cp T3 minus T2, highest minus lowest. So, this will be, let us call this as equation 1. Now, we know that we will try to represent these expression in terms of either compression ratio or cutoff ratio. We will talk about cutoff ratio, but let us, the idea is that represent all temperatures, represent all temperatures in terms of T1. So, we are just doing this because we want to eliminate all temperatures and try to write it in terms of compression ratio or cutoff ratio, like that. All right. Now, this can be further simplified. In fact, let us I will try to write this gamma as well. So, 1 minus, now Cp by Cv is gamma, I will send this gamma here. So, gamma T4 minus T1 divided by T3 minus T2. So, that would be better. Now, I will call this as equation 1. Now, represent all terms in terms of all temperature in terms of T1. Now, how do we do that? Let us start from process 1 to 2. Now, what is process 1 to 2? So, we will come back to this equation 1 later. Now, process 1 to 2 is P1 V1 power gamma is equal to P2 V2 power gamma. All right. Now, we want temperature and compression ratio. So, I will eliminate this PV is equal to MRT equation I will use, and in place of pressure I will substitute T by V, this we have been doing. So, in place I mean this MR cancels out. So, we will end up with T1 by V1 in place of P1. So, V1 power gamma and T2 by V2 power gamma. So, all right. So, then we will write T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. All right. So, then we have this T2 is equal to T1 V1 by V2 whole power gamma minus 1, and remember T1 V1 by V2 is R power gamma minus 1. Now, what did we just do is this, we have written T2 in terms of T1. We have written T2 in terms of T1, that is what the intention with which we started. Temperature, all temperature we will try to represent in terms of T1, all right. Now, similarly, let us write T3 also in terms of T1. Now, what we can do? Let us take next process, maybe we will take process 2 to 3, process 2 to 3, process 2 to 3. Now, what is process 2 to 3? I know that there is PV is equal to MRT I will use. Now, process 2 to 3 is a constant pressure process. So, V by T is equal to MR by P. So, the whole right side is constant. So, V by T is equal to constant. Now, what is V by T? V2 by T2 is equal to V3 by T3. That is what we mean by V by T is equal to constant during process 2 to 3. So, pressure constant or V by T constant, both are same. Now, I will go here and say that T3 by T2, I will send this T3 this side and V3 by V2 here. Now, what is V3 by V2 is very important. Now, V3 by V2 here, if you look at here, so this is the portion about which we have been keep on supplying fuel. So, up to that portion or up to that volume we are supplying the fuel. So, that is something like after this V3 we are cutting off the fuel supply. So, V3 by V2 very important, V3 by V2 is cutoff ratio, and let us denote this cutoff ratio as rho. Okay. Now, V3 by V2 is rho. Therefore, I can write T3 is equal to T2 into V3 by V2, that is nothing but T2 rho. But remember, we wanted to represent all temperatures in T1. So, T2 we already know. T2 is T1 R power gamma minus 1, and this rho remains here. So, because why did we write this here? Because we already know, maybe we will call this as equation 2. We know from equation 2, uh, T2 is equal to T1 R power gamma minus 1. All right. Now, this let us call this as equation 3. Okay. So, T2 and T3 both we have tried to represent it in terms of T1, we have done it. Now, let us go back to the next step. Maybe if we write T4 in terms of T1, then we can come back to equation 1. Now, let us write T4 in terms of T1. So, process I'll go for process 2 to 3 we are done, process 3 to 4. Now, process 3 to 4, what is process 3 to 4? P3 V3 power gamma, that is PV power gamma is equal to constant. So, PV power gamma is equal to constant. So, P3 V3 power gamma is equal to P4 V4 power gamma, and we know that we would like to represent it in terms of temperature. So, I know that PV is equal to MRT. In place of pressure, I am gonna do this MRT by V, and if I do that in place of pressure, I will have T3 by V3, V3 power gamma, T4 by V4, V4 power gamma, and then we will have T3 V3 power gamma minus 1 is equal to T4 V4 power gamma minus 1, or we can say T4 is equal to T3 V3 by V4 whole power gamma minus 1. And now we are at a situation, we have a ratio of V3 and V4. Remember V3 and V4. This is neither cutoff ratio nor compression ratio. So, V3 by V4 will have to solve it, like we use the technique, let us multiply and divide by V2. Which one? So, V3 by V4 we are trying to solve, alright. So, V3 by V4 multiply and divide by V2. So, we are not changing the meaning of this equation, we are dividing and multiplying by V2, alright. Now, V3 by V2 is what? V3 by V2 is cutoff ratio rho, V3 by V2 is cutoff ratio rho. Now, I will also write it here because that is very important term. V3 by V2 is equal to rho, that is cutoff ratio. Okay. So, V3 by V2 is cutoff ratio. So, that can be done. So, rho, and what is V2 by V4? Now, go back here, this is nothing but V2 and V4 is nothing but V1, alright. So, we know that V1 by V2 is compression ratio R, alright. A V1 is equal to V4. So, therefore, V4 by V2 is equal to R, but we are having here V2 by V4 is equal to 1 by R. So, this will end up with rho by R. Okay. So, V3 by V4 can be written as rho by R. V3 by V4 can be written as cutoff ratio divided by compression ratio. Now, I will come back here. Therefore, T4 is equal to T3 rho by R, and remember this gamma minus 1 and gamma minus 1 there only. Now, T3 we have already got in terms of T1. Let us go back to that expression, equation 3. So, from equation 3, from equation 3, T3 is equal to T1 R power gamma minus 1 into rho. So, now therefore, in place of T3 I write T1 R power gamma minus 1 into rho, and rho power gamma minus 1 is there. divided by r power gamma minus 1. This r power gamma minus 1, r power gamma minus 1 cancels out, and we will have T4 is equal to T1 rho, rho means rho power 1. So, gamma minus 1 plus 1, alright, because if we add the powers it will be rho power 1 and rho power gamma minus 1 plus 1. So, this minus 1 plus 1 goes off. So, T4 in terms of T1 will be T1 rho power gamma. So, now we have got expression for T4 also in terms of T1. So, we have got equation 3, I will call this as equation 4. Now, what is the idea? Equation 2, 3 and 4 in equation 1. Now, what was our equation 1? Efficiency is equal to 1 minus 1 by r power gamma minus 1, sorry 1 minus 1 by gamma, 1 minus 1 by gamma, and we had this T4 minus T1. So, in place of T4 I will write T1 rho power gamma minus T1. So, this T4 minus T1 in the numerator divided by we have T3 minus T2. Now, what is our T3? T3 is T1 r power gamma minus 1 into rho, T1 r power gamma minus 1 into rho minus T2, that is T1 r power gamma minus 1, T1 r power gamma minus 1. Now, what we can do is 1 minus 1 by, we can take r power, I mean we can take T1 common in numerator. So, rho power gamma minus 1. Similarly, we can take r power gamma minus 1 common in the denominator and also T1 in the denominator. So, we will end up with rho minus 1. So, T1 cancels out, we will end up with the expression efficiency of a diesel engine is given by 1 minus 1 by r power gamma minus 1 gamma, and this is rho power gamma minus 1 divided by rho minus 1. So, this is the expression for efficiency of a diesel engine, alright. So, this is the expression for efficiency of a diesel engine in terms of compression ratio and in terms of cutoff ratio, where we can write where R is compression ratio V1 by V2 and rho is cutoff ratio V3 by V2. Okay. Thank you.